Hello everyone and welcome to another video. In this video, I will be discussing geometry and the Pythagorean Theorem because I have not discussed geometry, but I discussed algebra and the distributive property before. So let's get into it. Introduction to the formula. So to the left, you see a triangle. This is the standard representation of a right triangle that I will be using during this presentation. Side length A, color-coded in blue, represents the adjacent length of the right triangle. Side length B, color-coded in green, represents the opposite length of the triangle. Finally, side length C represents the hypotenuse length of the triangle, and it is color-coded in red. The formula itself. The Pythagorean formula only works on right triangles, or triangles that have one right angle, but it can also be applied to other sorts of triangles under the right circumstances. For example, if you know the height of an isosceles triangle, you can imagine the triangle split into two right angles and two right triangles. The basic fundamental formula itself is a squared plus b squared equals c squared. You can see it in many different forms like c equals square root of a squared plus b squared, but they all mean the same thing. Now, what does this formula actually mean, and what does it tell the mathematician? Let's go to our right triangle that we saw in the first slide to find this out. Let us assume that the side length A is equal to 4 inches and the side length B is equal to 3 inches. Well, the following formula, it means A squared is 4 squared, which is 16. B squared is the same as 3 squared, which is 9. Now we have to follow the formula and add it up. 16 plus 9 is 25. Now 25 is c squared, but we want to find solely the side length c, not c squared. So what we have to do is the square root of c squared equals c, and the square root of 25 is 5. Therefore, side length c is 5 inches. Applications of the formula. With this formula, one is able to calculate the third length of a right triangle if they know two lengths. From here, engineers have utilized this formula to calculate how to construct buildings and sculptures. If you look hard enough, you will find examples of the Pythagorean theorem everywhere. In fact, the ancient Egyptians used this to get their pyramids built. I will show an example of how you can use this in the real world. Imagine that the image to the left is a blueprint for the house. If the architect wanted to know in advance what the length of the roof, highlighted in red, was, they would have to use the Pythagorean theorem. Familiarity with the formula. To practice using the formula in the following examples, find length C. What is length C when 1, a equals 4, b equals 3, 2, a equals 48, b equals 14, 3, a equals 12, b equals 5, and 4, a equals 8, b equals 6. You can pause the video to calculate these out. Congratulations! If you solved them, the answers were 5, 50, 13, and 10. Let's move on. Okay. Why does it work? Now that you can utilize such concepts, it's time to understand how these concepts actually work. The Pythagorean theorem can be proved with many methods, but my favorite, and in my opinion the most satisfactory way, is with something called proof by rearrangement. This is where you can rearrange shapes to get a more complete perspective on certain formulas. Let me show you how this one works. Starting off with 4 identical right triangles labeled in the same manner as all of the other triangles I represented in this presentation. We have side length C, side length A, side length B. Next, we rearrange all those triangles to create a square of length C. The area of this square is c squared. Notice how in this figure there are still 4 right triangles. We just rearranged them so length C is multiplied by length C to get an area of c squared. Finally, we rearrange the triangles once again to form 2 rectangles. Now we see a squared and b squared. How does this exactly prove the Pythagorean theorem though? Notice how in the figures above the area is the same, consisting of 4 triangles in both figures. The area of the total square, 2 times a plus b, is also consistent through both figures. This means that the blank space, c squared in the first figure and b plus a squared in the second figure, b squared plus a squared in the second figure is also consistent. From this, we can indeed conclude that a squared plus b squared is equal to c squared. Thanks for watching this presentation, and see you in the next video.